Hey everyone, thank you for coming. So my name is Ben.
And I'm Kaveh.
And today we'd like to talk to you about this new side channel attack that we have called TLBleed. So we're going to use the TLB to leak some secrets. And Kaveh can introduce to you now sort of the landscape of cache attacks, cache defenses, and I'll later on tell you about how TLBleed fits into that landscape.
Thanks, Ben. So who are we? We are part of FUSEC, so you might have heard of us. We are the security research group at the FU University in Amsterdam. So we do research on software security, but and then we do software hardening exploitation, but we also do hardware attacks and side channels, and this is going to be what we're going to talk about today. And here you can see Ben holding his Ponech plug, and you will soon see why. Alright, so this is the overview of the talk. I'm gonna quickly talk about cache attacks for those of you who are not familiar with them, and then a little bit about defenses that we are deploying these days against these cache attacks. And then Ben is going to tell you why all of these defenses are broken. And then we're gonna tell you how effective this new attack is. And then we're also gonna talk about a little bit about the reception. How people basically reacted to the discovery of the TLBleed attack. Alright, so what are cache attacks? So to understand cache attacks, you first need to understand what side channels are. And so if I want to basically introduce it, I would say like it is basically something, some mechanism that allows you to leak some secret information without you directly asking for it. And basically to make it more, to give a more real life example, we always use this thief who's trying to steal something from this safe, and this person who's basically wearing a stethoscope trying to listen to how the lock is sounding whenever you try to basically figure out the combination. Now if you want to go through the real channel, right, you have to brute force it, right, and it would take maybe days if not years, right, and then of course the burglar doesn't have this much time. So, and basically by just listening through the mechanism in the lock, the burglar could figure out what the combination is. And there is a shared channel between the burglar and this mechanism in which the secret is being leaked, the secret being this combination. And this shared channel is the air, right? So it's a sound, right? And then there is this air which is shared, and then this basically through this air the sound basically gets leaked, and then suddenly you can figure out what the secret is. So this is in a real world, but okay, so what happens inside the CPU? And for that we need to understand what is being shared, right? So if you now go and buy an Intel CPU or an AMD CPU, well, this one is specifically an architecture of an Intel CPU, so if you buy one, and you basically try to understand, to look at the architectural diagram, you find out that it basically is architected in such a way that you have multiple cores, right? And these CPUs these days are all based on the von Neumann architecture, which means that you have memory which is far away from the CPU, but it is very slow. So to make it fast, you start having caches right in between. And the faster, the closer to the CPU, the faster you want these caches to be, which means that they have to be smaller. So this is like basically the fundamental way in which caches are designed. If you want them to be fast, they have to be small. But as you start like going further away from the cores, you start to share more and more. So for example, at the lowest level, the last level, you have a cache that is shared in between cores. So basically a core could use some part of the L3 which is also used by another core in the system. So this is being shared between these cores. And from my previous examples, now you immediately can see that this could lead to some problems, right? And you might also wonder, like at the upper levels, for example, if you look at this L2, what else could be shared? So if you look at a core, so this is not just a single execution context. Oftentimes you have now threads in hardware. So you have these things that are, Intel calls them hyperthreads, right? That are basically sharing these upper level caches like L1 and L2. All right, so and you use these shared resources to build side channel attacks. So it is not just the CPU caches that I just told you about, but also your memory is shared between different execution contexts. Your TLB is also shared, which is a different cache, which we will get into soon. And using all of these shared resources, basically you can leak information. But it's not always the case that you want to leak something. Sometimes you don't want to allow two different processes, for example, to communicate with each other directly. But by using this shared medium, they could indirectly communicate with each other. So if there is a shared medium and I start to use it, then the other entity that wants to use this wouldn't be able to use it as fast, for example. And this principle could be used to build a communication channel. So whenever I want to send a 1 bit, I start using it, and then the other entity will know that I'm using it. And this means that I'm sending a 1 bit, right? And but sometimes, so this is fine. This means that both of these processes are cooperating with each other, but the more interesting case is when one of these processes is just a victim that doesn't know what is happening, and then the other process tries to understand what this victim process is doing. And this is what is known as the side channel attack. So basically allows the one entity, the attacker entity, to spy on the other entity. So to basically make this a little bit more concrete, I will give you an example, a very famous example, which is called the flush and reload attack. This work has been published by Yuval and Katrina, and I explain how this works. So here on top we have an attacker process and a victim process, and then the attacker is doing a bunch of operations to figure out whether the victim is doing a certain memory access or not, right? And then later I will basically show you why this detection of whether the victim is doing a memory access is good enough for the attacker to figure out basically a cryptographic key. So here's what the attacker will do. So the attacker will flush a certain part of the cache, right? One part of the cache. And then the attacker waits for a while, right? And then the attacker tries to access that location in the cache again. Now, because the attacker has flushed this location, if the location is still flushed, the access is going to be slow. And so in this case, the victim is doing something else, is not doing access at that memory location, which would mean that basically the access has not happened, right? In the second case, right, the attacker does the same thing. It flushes the cache. But in the meantime, the victim does a memory access this time. Now, this would mean that this location is now cached, right? And then the attacker tries to check whether this location is cached or not. And this time, because this the memory location is now in the cache, this operation happens faster. And now the attacker could detect that basically the victim has performed a memory access. You can use this to, as I said, attack a cryptographic implementation. Here, for example, assuming an AES implementation that uses T-table, I'm using a lot of words that you may not understand, but the thing that the only thing that you need to understand is that the attacker just tries to understand whether this table has been accessed or not. So here you have a table, and basically the location in which table which is getting access every time this AES operation is happening depends on the secret key and the input that the attacker could provide. So you give a plain text, and then depending on the bit of the key, some location in this table gets accessed. And now using the primitive that I just told you about, the attacker could figure out basically which location in this table is accessed. And since the attacker, we assume that knows also the plain text, it could basically figure out the secret bit. So the secrets are, by the virtue of this memory access, the secrets are being betrayed. And by controlling the plain text and looking at the memory access, you can recover the key. So you might wonder how this looks like. And here, for example, the attacker could detect these bytes. So like these are the latency measurements. And like if it is black, it means that basically it was quite a fast operation. And basically by doing these measurements, you can figure out basically that given the plain text, which cache line was accessed. And this allows you to leak the secret value. And so we have another example for you where we visualize these like accesses in the cache. So, and this example uses the LIBGCRYPT ECC point multiplication, which is another cryptographic routine. And basically it works like that. So don't look at all these code that is there. The only thing that you need to worry about is this basically routine that gets basically gets executed, and it depends on this scalar which comes from your cryptographic key. And if this bit is set, then basically there is an addition operation that happens, right? So If we can detect whether this addition operation is happening, it means that this bit location is 1, and otherwise it's 0. So let's look at basically when we give an input to this function, how does it look like from the point of the cache. So this is how it looks like. So the blue one is if the key bit is 0, and the green one if it is 1. Obviously, you can see that whenever the bit is 0, the operation is shorter. But more importantly, whenever the bit is 1, also the type of access patterns that happen is a little bit more different. And to actually understand this a little bit better, we have tried to basically put them back to back to see how they look like. And they look like this. By the way, the upper part is data, I think, and the lower part is code. So here, for example, you can see that the blue part is basically when the bit is 0, and the green part is when the bit is 1. So operation takes longer. Now, it might not immediately be obvious for you the difference into this. So you need to do some statistical analysis, and Ben gives an example of this statistical analysis when he talks about his TLBleed attack. The only thing that you need to believe me on is that there is a difference between these two. All right, okay. So now let's look at, so people of course realize that this is a problem, and let's fix this, right? So they try to change the cryptographic function to make it more constant time. And so when we execute the one that is actually safe, the accesses all look like this, right? So it looks like they're all the same, and we would not be able to actually see the signal from this bit key that is 1. But actually, what they do is that they do all this operation as if, you know, regardless of the bit in the key, but at the very end, they only commit the results if the bit is 1. Right? So instead of you seeing all this like operation all the time, you see it at the very end. So if the bit of the key is 1, there is some little operation here that happens that is a little bit different. And using this at the very end, instead of happening all the time, we could still figure out that the key bit is 1 or 0. And so the result of this story is that the moral of the story is that this is actually not so easy to build constant time cache implementations. So we have realized this, and we have started like coming up with more protections against this. So forget that like the software could not do this in a safe way. What if we could build some protections in which if we run some software, some piece of code, then it will always be side channel free. So regardless of what the software is doing, could we make it in a way that it will be protected against these cache attacks? So that's what the defenses come into play, where the defenses come into play. And I'm going to tell you a bunch of these examples of these cache defenses. So the first one is, it basically tries to partition the cache. Here you can see the first diagram that I showed you earlier. And here you can see that the L3 is shared between these cores. So assume that I want to protect the first core from the second core. What I can do is I can partition my cache in a way that core 0 does not have access, for example, to the part of the cache that core 1 could access. So if I make this perfect isolation between these two, then I cannot do a cache attack through L3, for example. Let's see how this is done in practice. This is, by the way, a technique that is most commonly known as cache coloring. And the reason why they're called color is so like to make it easier to understand. What you want to figure out is how your memory addresses are mapped to cache locations. And since there are a limited number of cache locations, you could attach a tag to it and call it a color. So you could say like, okay, I have a color blue, and all these memory addresses in the system would map to color blue, right? And this is how it would look like. So if you can figure out this mapping between your memory addresses to cache locations, you could basically partition the system by giving different processes different memory addresses. So they would map to different parts of the cache. And then if you do this, then say if one process only has access to color blue, then basically the red process would not be able to interact with the part of the cache that is allocated to process that is blue. And this basically prevents this sharing of resources between these two processes. Now this could stop cache attacks, but the problem is that now you have so like some limitation in terms of how your kernel or your operating system could allocate memory to different processes in the system. And so this limitation basically makes it quite complicated to write memory management code. I don't know how many of you have tried to understand or fiddle with memory management code. If you have, you know that it is quite, already as it is, it's quite complicated. So if you want to add more constraints to it, it becomes suddenly much, much more complicated. So people typically don't like to do this. Just to give you a little bit more information so that when Ben starts introducing TLBleed, you would understand the attack a little bit better, I will try to explain how this mapping between memory locations to cache locations happen. So basically, your caches are partitioned in what we call sets. So here, we are basically showing different sets as this, basically horizontal boxes. So here is one set, here is a second set, and so on. And each set will have some spaces. So some space, it has a size in which number of entries could go to this set. And if you access more memory locations that map to this set, you need to kick out some other entries from this set to make sure that there is a space for the other one. And this is known as ways. So if you have, say, 8 cache sets with 2 ways, it would mean that your memory address could go to any of these 8 cache sets, but not more than 3 of these memory locations that map to the same cache set could basically remain in the cache, no more than 2. So if you have a third one wanting to access the same cache set, you have to, by construction, remove one of those previous elements. And this is something that is known as cache eviction. Ben will talk about this a little bit more. So this is how cache coloring works. And yeah, by the virtue of this separation, then the different processes would not be able to look at each other. This is not working. All right. So the other protection, so as I said, like this is something that is difficult to do. You need to change your the core of your operating system, which is not something easy. And people have tried to solve this problem, right? And how do you solve this problem? You rely on your hardware to basically provide you with the same support. And so there is this technology that is called cache allocation technology that is an extension by recent Intel processors. And if your CPU has this support, you could use it to do partitioning of your cache. And so this was originally introduced by Intel so that you could provide quality of service to your virtual machines in the cloud. So if you run virtual machines and then suddenly like one virtual machine could basically occupy the entire cache, get all the performance, and then the other virtual machine would basically have very little performance, bad performance, right? You don't want this to happen. Intel came up with this technology to make sure that you statically partition your cache so that this wouldn't happen. And now, basically, what we could use this technology to also provide some security rather than basically just isolation. So it is basically a hardware feature that you rely on. So assuming that this is your cache again, and you have your basically 2 processes that you have in the system, what you could do is that you could partition your system using partition your cat using the number of ways. So here in this example, we have 2 ways, which means that we could partition only 2 processes in the system, right? In reality, the number of ways is a little bit more. For example, if you have a normal L3 system, it's oftentimes 12 or 16. So here, now, each process could access anywhere in the memory, but basically the partitioning happening at the way level. But it could only host one of these entries in the cache sets. So now using these, now one process cannot spy on the other. But this would mean that now, even though if there are, even though you have like different number of ways, you can only access a certain limited number of ways, right? And since you have a limited number of ways, it would mean that since you're partitioning your cache in a very coarse way, your performance is also going to be bad. And this is also something that you may not want. The other thing is that the number of these ways in your system is kind of limited, right? So it's like 12 or 16. So it means that you could only have 12 security contexts in your system. This may also be a limitation that you may not want. So people have realized this, and they have come up with a second technology that is called the TSX. And what is TSX? It's another extension by Intel that provides support for hardware transactions. So, and how would this work? So typically, you want to have support. So sometimes you want, so you've written some piece of code, and you always want this piece of code to execute it in its entirety. So if you're executing some piece of code, and at some point you realize that something has gone wrong, you want to roll back all of this computation to the point that you started the transaction. So those of you who have written banking software, for example, you know that this is something that is very useful, right? You don't want a transaction of a customer to abort at some point and still you have deducted the money without that person having gotten the money from the ATM, for example, right? So you want this operation to happen in its entirety. Either I withdraw the money or I don't. The value in my bank account shouldn't change if I don't, right? And so this is how Intel tries to provide support for these kind of operations. And the idea is that since this whole thing happens inside the CPU, you want to make sure that all the write and reads that your transactions are doing remain in the CPU cache. And this is what is called the transaction working set. And if this transaction working set, basically you go over the amount of cache that you have available, automatically you will get an abort because the processor can no longer ensure that your code runs in a transaction logic. And you could also use this principle to build your defense, right? Because the attacker, remember, needs to basically flush parts of your cache, right? And then if you see that you're getting an abort because of this, then so this signals that there may be something fishy going on. So you could use this to detect that there is an ongoing attack. So we can use this as a defense. And yeah, so people have done this. And so this is the same figure that I showed you earlier. And if you actually run it inside a TSX transaction, you can see that the signal gets diluted quite heavily, and then you can no longer detect that there was an access inside a certain location in your T table. So now that I've basically told you about these cache defenses, so this is where we started last year when we started thinking about it. So, okay, are we done? Have we fixed all of these problems with cache attacks, right? And then so we were looking at the instruction manual of Intel, and then there we realized that, okay, there is a TLB, right, that is also shared between different execution contexts, actually between different hyperthreads, which Ben is going to talk about. And the thing that you immediately think about when you want to think about these attacks is that how many sets are there? Are there actually sets in the TLB? So this is the first thing that basically comes to your mind. Then looking at the instruction manual, it basically was written there that there are actually sets. So we know that we are onto something, right? So we started this journey that would lead to this discovery of this new attack. And during this journey, the thing that we discovered is that actually the sets don't matter, right? So we had to, due to the limitations that we had to come up with a new attack that would not matter whether you have sets in your TLB or not. And I now hand over the presentation to Ben to explain the new attack that he had to come up with to actually be able to leak stuff, even though you have only a single set that you could leak your data from.
Great. Great. Thank you, Kaveh. All right, so let's talk about this TLB business. So as Kaveh explained, there are many shared resources in a system. We have the RAM, we have the cache, and whenever you have a shared resource, there's this risk of a signal leaking from one protection domain to another, which is supposed to be impossible, right? There's supposed to be this perfect abstractions, but because of all these shared resources, we realize these abstractions are actually quite porous. It would be very nice if using these generic cache defenses, these cache side channels would be gone, but and to a large degree that is true for cache attacks, but it turns out that if you use different shared resources, this problem returns, even with deployed cache defenses. And we can exploit the TLB to also leak secrets. Okay, so let's see how this works. So by a show of hands, who here knows about how page tables work? Great. Okay, I can see we're in a room of experts. Okay, so let's just go over quickly about this idea of page tables. So CPUs constantly handle addresses. They're executing from a particular address, they're loading data from an address, they're storing data into an address, and all of these addresses are what we call virtual addresses. That's the point of virtual addresses, is to give every process the pleasant illusion that they have a 64-bit, this huge 64-bit address space, completely private to them alone. No one else's memory is in there, and your own memory, unless you want it to be, is not in anyone else's address space. So you kind of have this illusion of the machine to yourself, hence the idea of virtual. This abstraction is created by the operating system which assembles a data structure called page tables, which is a mapping from this huge sparse virtual address space to the real physical address space, which is not sparse, it's just, you know, on RAM chips. And the mapping, whenever the process changes, this mapping changes also. The operating system takes care of this. Now, this is a beautiful mechanism. It has very powerful properties, but it's also, if you have to look up this translation every single time you handle an address, which is all the time, it would be very, very slow. So therefore, all these translations are constantly are cached very aggressively in this caching structure called the TLB. TLB is short for Translation Lookaside Buffers. So the CPU is constantly accessing the TLB because it constantly needs to translate from virtual addresses to physical addresses. So what if the TLB were shared between CPUs, maybe between cores or between hyperthreads? If that's true, then the activity of one thread would be visible to another thread just because of the fact that they're sharing TLBs in exactly the same way as we can leak activity through the cache. So what we know is that, so let's try and find out about this. So what we know is that TLB has two levels, level 1 and that's in the documentation, right? So we have, just like the caches have levels, the TLB has levels, which is a faster level 1, split in instructions and data, translations of course, and level 2, which is much larger and a little bit slower and shares instructions and data. And in exactly the same way as caches are partitioned into sets which have a set size called the number of ways, the TLB, we expect, is partitioned in a very similar kind of way. But we have no idea what the structure is because it's not documented. By the structure we mean if I take a particular lookup into which set or slot, into which set is this going to go into the TLB. In other words, I want to be able to predict when I access a set of addresses, which can I cache at the same time and which can I not cache at the same time because the set that they go into overflows. That's what I have to know to monitor TLB activity. So let's look at this TLB as just another cache. And as Kaveh was saying, this is a representation of how a cache might be structured. So if you imagine that all of these things are RAM cached lines, right? These RAM blocks can go down for billions in the downwards direction. But there's only a limited number of cache cells that these items can be cached into. They all have to stay in the same column because this is the first blue, this is the first blue cache set. This is the first blue cache set, the second blue cache set, the third blue cache set, and you can't go from here to here. You have to stay in your own column. That's just a limitation of the hardware. And any of this column, will, as Kaveh was saying, has 8 or 16 or so entries, the wayness, the number of ways that we have. So as you can see, this structure, what we mean by the structure is that this column, if I take any of these blocks, how do I, to which set is it mapped? So let's try and find out about that. So let's just assume that the mapping is linear, just as we saw that just now. Like the first column goes into the first set, second column goes into the second set, and so on. And that the physical addresses were laid out 1, 2, 3, 4, 5, 6, 7, 8, 9, just in this linear mapping, and that goes into these sets in kind of this nice round-robin fashion. Doesn't have to be that way, but let's assume that's the case and see if that an experiment that we can make bears out this hypothesis. So let's try and find for this for the L1 DTLB, how many sets do we have and how many ways do we have under the assumption that we have a linear mapping. So we try many possible combinations of how many sets do we have from 0 to 80, how many ways do we have, what is the set size from 0 to 20, and we assemble eviction sets that would fit perfectly into this TLB if it were that size for all these combinations, access them over and over and over again, and using performance counters we measure, well, do we get a TLB hit or a TLB miss? And what we expect to see is that when we have the exact right configuration, we see no misses, but when we go 1 over, then we start to see misses. So what we see is that the smallest set size where we can see any misses whatsoever is 4. That's here. And the smallest number of sets corresponding to these misses is 16. So what we see here is that the hypothesis of the L1 DTLB having a linear mapping with 16 sets and 4 ways each is the one that holds. So using experiments like these, we can reverse engineer the structure of the L1 DTLB, ITLB, and with slightly more complicated experiments, we can reverse engineer the structure of the L2 TLB as well, because sometimes it's not linear. What we find is that starting with the Skylake microarchitecture, we take the page number, because it's all about pages, right? And we have to XOR the lowest 7 bits of the page number with the next upper 7 bits. We XOR them together to get a 7-bit number, so 0 to 127, to get the slot number. So it's not linear, but it's sort of a simple approximation. This is, if you were to use modular 2 arithmetic and you multiply the page number by this matrix, then you would get that output. Broadwell does something very similar, but it then uses 8 bits instead of 7 bits to XOR together and get the result. So using these techniques, we find lots of different properties of the TLB. What we want to know, in order to be able to do anything at all, is are these TLBs shared at all between hyperthreads? But now that we know how to reverse engineer the structure, we do this experiment where we completely access set 0 on one hyperthread and set 0 on the other, and see if we get any evictions, if we see any misses. And we try all combinations from 0 to 15 on one thread, 0 to 15 on the other thread, and what we expect if we see sharing, that where we see misses depends on what the other thread is doing. And we find for the L1 DTLB, yeah, we see exactly what we were hoping, which is that 0 interferes with 0, 0 on one thread interferes with 0 on the other thread, and set 15 on one thread interferes with 15 on the other thread. We tried exactly the same thing on the ITLB, and we see no such sharing. So we do not see any activity on one thread that depends on activity in the other thread, unfortunately. So on L1 ITLB, we see no sharing. For L2, we do see sharing, but we see this interesting little shift. So we find that set 0 on one thread does not interfere with set 0 on the other thread, but with set 64. So there's this kind of, apparently in the hash function, it seems like maybe we include the hyperthread thread ID in this hash function. Therefore, slot 0 interferes on one thread, interferes with slot 64 on the other thread. I don't exactly know why this happens, but what we think that might be the case is that this evens out the TLB activity from one and the other. If it sort of might spread it out more over the whole TLB, you might get more contention otherwise. That seems to be the purpose of these unusual hash functions. Okay, so using experiments like these, we reverse engineered many properties of the TLB. So we have here a list of microarchitectures, and we find, well, how many sets do we have? How many ways do we have? We find that for the DTLB, it's always 16 sets and 4 ways. Hash function is always linear, and it's always shared. For the ITLB, we find that associativity, as we call it, has gone up. So we used to have a 4-way 16-set cache, and it's gone up to an 8-way 8-set cache, which is better. We have the same number of entries, it's both 64, but because the associativity is higher, we will see under the same workloads fewer evictions, because the partition is larger. And we find that for the L2 TLB, we have this weird XOR function that started with the Skylake microarchitecture, and before that it was linear as well. Okay, so that's interesting. So we understand the structure. We know there is sharing to a degree. What we have to find out now is how can we observe this signal without performance counters? Because performance counters we can't use because we need a system call for that. They're too slow and they're privileged. So we assemble eviction sets that exactly cover the L1 DTLB and the L2 TLB and mist them all together. So these 3 versions, and we want to see just by timing the access latencies whether if we hit one or the other or miss it altogether, which means we have to do a page table walk. And if we measure the latencies, can we distinguish one from the other? And what we find is that, yeah, it seems like from the timing latency, we can tell the difference between a hit and a miss in the L1 DTLB. So we can use the L1 DTLB as a method to observe activity on the other hyperthread. So that's interesting. So let's go back to this case study of this ECC multiplication function. When we're going to use this as a case study to see if we can leak the secret bit, that we're processing, the secret bit being in the scalar function. This is the non-side channel proof version, but as we've talked about, if there were a generic cache defense deployed, this would still be safe. So let's see if a generic cache defense is deployed and we run this code, can we still leak this data through the TLB or not? So let's see what that would look like. We can only use the data access as a distinguisher. So a simulation of how this might look like is this. So if we look at the background shade is if the secret bit is 0 or 1. And the activity is now, instead of using the cache, we look at the TLB set activity. So what we see is that you can see some kind of difference, but it seems like that every set is active either all the time, all the way throughout green and blue, or neither, nor green nor blue. So there's no easy distinguishing feature here that would let us see one or the other. So let's see a simulation of that. Let's see a better simulation of that. Yeah. So this is a cache trace similar to the one Kaveh was showing you, but instead of the cache trace, it shows you the activity in TLB sets. So that means there are fewer of them. And the spatial granularity is much lower because we're talking about, so in the cache we have 64 byte cache lines, but these are 4K pages. So we have much less information going for us. So I don't know about you, but if I look at this, I can't really tell a difference much in blue or green. Yeah, I can tell green is longer, of course, but we can't really use that information because as an attacker we can't see length. We can only see patterns. So this is quite tricky. So we want to be able to distinguish green from blue using just a signal like this. Okay, so let's try and do this, even though it looks hard. What we can see, even though it looks hard, is that patterns like these are different, right? They're a little bit different in time. So I see this axis pattern when it's green, always, and this axis pattern, which is, fewer dots together, when it's blue. So can we maybe exploit this temporal signal in an attack? So let's monitor a single TLB set and use this temporal information, or try and use this temporal information to recognize, are we in a blue area, a blue shaded area, or in a green shaded area, which corresponds to the secret key bit, don't forget. So can we distinguish 0 from 1 using this technique? So this is a real attack scenario. So we have a spying process which monitors one particular TLB set over and over and over again, and the latency will be low always unless the victim is doing something there. As soon as the victim does something there, the latency will go up because it means our own TLB entry is gone. So this is what it looks like. So we have no activity ping. So this is the victim does something, nothing, victim does something, nothing, and so on. So this looks quite noisy, so I can't really tell the difference between blue and green, but if you take a moving average, just to make it kind of easier on our human eyes, then we can start to see some regularity there, certainly for the blue case, and we can kind of tell that the green case is at least different in some way. It seems like we could have a chance to distinguish these signals as long as we don't have to do it by hand. So let's try and train this using machine learning. So we take this SVM classifier called this is the support vector machine. I'll briefly show you what this looks like. So this SVM machine learning classifier we can train by so it tries to distinguish training samples, and this is the training phase. You showed a bunch of green dots and a bunch of blue dots, and features that it have, and you tell them, okay, I want you to tell me in the future, is this green or is it red? And this algorithm will try and find the best separating line or plane if there are multiple features, or a hyperplane if it's even more features. This is an example with only 2 features. We're going to give it a sample with hundreds of measurements. It's going to be 100-dimensional vector space. Doesn't matter. The same concept applies. We're going to try and separate it linearly using this to be found hyperplane given a training set. So can we do that? This is the output that we get. So we see this classifier is able to distinguish extremely well, given some training examples, start of blue, start of blue, start of green, start of blue, start of blue, start of green, which exactly corresponds to the secret key bits. So that looks very, very promising. Kaveh, can you tell me how well this thing works?
Yes, of course. All right. So how well does TLBleed work? So this was like we went on and implemented all these attacks, and remember all those defenses that that we talked about, software defenses and also hardware defenses. So we wanted to know whether TLBleed, bypasses all these defenses. So the first experiment that we run is basically just we picked a bunch of CPUs with different microarchitectures, right? And then we generated a number of different cryptographic keys. And then we wanted to see if we do the TLBleed attack on this LIBGCRYPT function that we earlier showed you, out of how many times could we actually leak the key. And so remember that this is like a statistical analysis, so sometimes you don't exactly get it right. But then most of the times you have to like either repeat or you have to brute force a large number of potential bits that you have actually misclassified, right? But it turned out that this attack has a very, very high success rate. So here, for example, you can see that out of 1,000 cases, we could successfully identify the key in the bits of the key in like 998 of the cases. And so this basically was quite a good result. And sometimes, of course, the keys, some bits of the key we misclassify. So the question is, can we brute force for the actual key? And here is basically on the right side is like the median, on average, how many of the bits still require brute forcing. And you can see that it's actually on average quite a low number of bits that we have to brute force. And so all of this only happens quite quickly, actually, so 1 millisecond, right? So if you can just get a capture of 1 millisecond out of your operation, your cryptographic operation, this is enough for us to do about 17 seconds of analysis to actually figure out the key. So which means that this is quite a practical attack, right? So some of the attacks that you see in the literature, like sometimes would take like hours or days of analysis, or we require you to get a trace out of 15,000 cryptographic operations. Here we just need like 1 millisecond of operation to be able to actually identify the key. And so the number of brute force, so this is the median. You may wonder like how many attempts you may need. So in most cases, as you can see and as this number shows, it's actually quite low. Sometimes we need to like brute force about 4 billion. So when it is like 32 bits out of like a large key that we don't know, we need to brute force quite a bit. But this is still quite doable. So it would take us maybe like I don't know, the longest case it would be in the matter of minutes that would allow us to actually do the brute force successfully. Now I talked about like these hardware defenses that people have deployed. And here is one example, the CAT, remember cache allocation technology, and here it shows that TLBleed basically still successfully recovers the key. We have more experiments against these, so like protections, both cache coloring and also TSX. If you want to know more, please go ahead and read our paper. All the experiment results are there. All right, so how did people react to TLBleed? So we filed the advisory with Intel saying, hey, look, we found this new side channel that would allow us to leak information. So, and Intel took like, I don't know, 2 months or so to come back to us and say, this has the same power as a cache attack, and since they haven't solved cache attacks, it doesn't matter that you could also do this with the TLB. So this was the response that Intel gave. So, but some people who would maybe take seriously, a little bit more seriously, like OpenBSD, like, so Ben was in contact with Theo Derat, so like a main committer of OpenBSD, and he decided that basically TLBleed has enough impact for it to justify to disable hyperthreading by default on OpenBSD platform. And we were also talking with Red Hat, and also because of the discussions with Red Hat, they decided to provide this option so that you could automatically disable hyperthreading if you like. So we thought that this was quite a good academic exercise, but yeah, so the media thought that this is more than an academic exercise. I think especially because OpenBSD disabled hyperthreading, so they start like getting in touch with us and asking basically what is the impact of this. So there were lots of communication to the media, and so we don't usually create logos for our attacks, but so their register was so this was a communication with OpenBSD, was nice enough to actually create a logo for us. So this is the logo of TLBleed. It's just 2 hearts with some blood leaking. And yeah. And yeah, somebody went through the hassle of creating a Wikipedia entry. I don't know what happened for us. Yeah. So to conclude, we presented to you TLBleed, which is a practical, reliable, and high-resolution side channel attack, more than any that has been known before. So we could get quite a lot of samples. That's why Ben could do this like temporal attack. They bypass these TLBleed attacks bypass all existing known cache defenses. And yeah, so if you want to know more about this attack and generally discuss side channels, you can find us on Twitter. This is our Twitter handle. And if you want to reach the wider group, you could also use our group handle. And this is the website in which we publicly publish all the attacks that we do. So this is the talk. This is the TLBleed. So, and we are happy to take questions if there are any. Thank you.
Hello. Yeah. Thank you very much. I think we have time for a quick question, and then we can move into the panel. Anyone has a question?
Yeah, that's a very good question. It's tricky because the TLB is so. If you allow this sharing, if you allow the sharing unlimited, then it's basically impossible, because if you were to try to do isolation in software, it would restrict the virtual address space of the process that's running too much. So that won't work. So what you would have to do is either play tricks to scheduling so that you don't allow this concurrent access by two mutually distrusting processes at the same time. Maybe you could introduce a system call level facility that would temporarily inhibit the scheduling of other processes on a sibling hyperthread. That something like that would work. Of course, a very heavy measure would be to disable hyperthreading, which has significant drawbacks because hyperthreading does allow much higher utilization of silicon ultimately than without. And what the most realistic attack scenario is probably that of cloud provider. So if multiple VMs on the same machine, and that's the most realistic scenario, I think, that would allow two different parties on the same CPU at the same time. What should happen in that case is that they should not be scheduled on the same CPU at the same time, and I think that is the most realistic balance to strike. Do you think that's a complete answer?
Yeah, I think so. Yeah, either disable it if you don't care about performance that much, or try to do your scheduling right, I guess.
Does that answer your question?
Yeah, I got there's some way to get with that. More details, I think we need to look at that.
It's one of these things, I think, that you have to choose between sharing for performance or not sharing for security, and that depends on the situation.
All right. Thank you very much for your talk, and we'll have a short break because we need to set up the chairs for the panel, so you can sit here or, I don't know, breathe.
If you have more questions, please come to us. Sorry.
Yeah. Thanks.